Hi friends, today I am giving a lecture on decimal to binary conversion in digital logic design or switching theory and logic design. In the previous video, we are already discussed about how to convert the given binary number into equivalent decimal number. Okay. Now in this video, we have to discuss about how to convert the given decimal number into equivalent binary number. Okay, to convert the given decimal number into equivalent binary number, for that purpose, we have to use one method called double-double method. In the double-double method, we have to use two methods. One is successive division by 2 method. Second one is successive multiplication by 2 method. Okay. First method, successive division by 2 method. This method is used for converting the given decimal integer number into equivalent binary integer number. Okay, that means to convert the decimal integer number into equivalent binary integer number, we have to use successive division by 2 method. The second method, successive multiplication by 2 method. This method is used for converting the given decimal fraction number into equivalent binary fraction number. For that purpose, we have to use successive multiplication by 2 method. Okay, so now we observing this example. This is a decimal integer number 13 base 10. Okay, this is a decimal integer number. To convert this decimal integer number into equivalent binary integer number, for that purpose we have to use successive division by 2 method. Okay, in successive division by 2 method, the given decimal integer number is successively divided by 2 until the quotient is 0. This is the quotient. 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 Okay. The given decimal integer number is successively divided by 2 until the quotient is 0. Okay. Whenever the quotient is 0, these are the remainders. The remainders can read from bottom to top. So then we are getting the equivalent decimal integer, equivalent binary integer number. Okay. So now this is the 13. Okay. 2, 6. Quotient is 6 and the remainder is 1. Okay. 2 3's. Quotient is 3 and the remainder is 0. 2 1's. Quotient is 1 and the remainder is 1. 2 zeros, quotient is 0 and the remainder is 1. So these are called the remainders. Okay, this decimal integer number is successively divided by 2. Okay, until the quotient is 0. So whenever the decimal integer number is divided by 2, whatever the remainder we are getting, the remainders are right. Okay, beside the quotient. Okay, so 2 6, quotient is 6 and the remainder is 1. 2 3's, quotient is 3, remainder is 0. 2 1's, quotient is 1, remainder is 1. 2 zeros, quotient is 0, remainder is 1. Whenever the quotient is 0, then we have to stop the successive division by 2. Okay, then the remainders can be drawn from bottom to top. Okay, so 1 1 0 1. So 1 1 0 1. Okay, so the last remainder bit can be acted as MSB bit. Okay, this one is this one, this one is this one, this 0 is this 0, this one is this one. The first remainder 1 can be treated as LSB bit. Okay, so whenever the remainders can read from bottom to top, then we are getting the equivalent binary integer number. So this is called as successive division by 2 method. Okay, now we go for second example. So this is a decimal fraction number. Decimal fraction number. To convert this decimal fraction number, so we have to successively multiply by 2. Okay. Now 0.75 into 2, that is equal to 1.5. Okay. Now we are taking the integer part separately. We are taking the fraction part separately. So 1.5 integer part is 1. We have to separate it. After separating the integer part, what is the remaining part? That is 0.5. Now we are taking 0.5. So 0.5 is multiplied with 2. So that is equal to 1.0. We have to separate the integer part. So this procedure is stopped until the fraction part is 0. Until the fraction part is 0. So 0.75 into 2 is equal to 1.5. We have to separate the integer part and fraction part. Integer part we have to write it. So what is the remaining fraction part? We have to take this remaining fraction part is multiplied with 2. So that is 1.0. So the integer part can be separated. What is the remaining part? Fraction part, that is 0.0. Whenever the fraction part becomes 0, then we have to stop the procedure. Now whatever we have to write the integer parts, that integer parts can be read from top to bottom. Top to bottom. Then we are getting the final equivalent binary fraction number. So this result can be written as after the decimal point, because we are taking the fraction part, decimal fraction part. So 0 point. Now we have to read the integers from top to bottom. So that is 1, this one is this one, this one is this one. So 0.75 base 10 is equal to 0.11 base 2. This is a binary fraction number and this is a decimal fraction number. Okay, whatever the first integer 1 we are getting, that one can be treated as MSB bit. Last one can be treated as LSB bit. Okay, so this procedure is called as successive division by 2 method for converting the given decimal integer number into binary integer number. Okay, now this method is called as successive multiplication by 2 method. This method is used for converting the decimal fraction number into equivalent binary fraction number. Okay, by combining these 2 methods, okay, by combining these 2 methods, successive division by 2 method and successive multiplication by 2 method. By combining these 2 methods, we have to convert the given decimal integer and decimal fraction number into equivalent binary integer number and binary fraction number. Okay, to solve this type of problem, so this problem contains one integer part and one fraction part. Okay, this is the integer part and this is the fraction part. Okay, so it is a mixture of decimal integer number and a decimal fraction number. To convert this mixture of decimal integer number and a decimal fraction number, so we have to separate this number into decimal integer part separately, decimal fraction part separately. After solving these 2 sub problems, then we have to combine the result of 2 sub problems, then we are getting the final result. So here 13.075. So we have to separate it is decimal integer number This part is decimal fraction number. Okay, decimal integer number is this subproblem. Decimal fraction number is this subproblem. So these two subproblems can be solved independently. Then whatever the result we are getting from two subproblems, then we have to combine them. So here the result is 1101. Here the result is 0.11. Now we have to combine it. We are getting 1101.11 base 2. So this is the resultant value of resultant binary integer and fractional number for 13.075. This is the decimal number. This is the equivalent binary number. So this decimal number contains two parts. One is integer part and another one is fractional part. Okay, we have to divide this entire number into decimal number separate, decimal fraction number separate. So whatever the result we are getting from these two parts, then we have to combine. Then we are getting the final binary equivalent number. Okay, so in this way we have to solve any decimal integer and fraction number into equivalent binary integer and fraction number. Okay, now we go for some example problem in the next video. Now in this video we have to solve some example problems on decimal to binary conversion. Okay, now we go for first example. Convert 52 base 10 to binary equivalent number using the double dowel method. To convert this given binary decimal integer number into equivalent binary integer number, we have to use successively division by 2 method until the quotient is 0. Once the quotient is 0 is obtained, the remainders can be read from bottom to top. Then we are getting the equivalent decimal binary integer number for decimal integer number. Okay, now we have to take 52. So 52 decimal integer number is converted into equivalent binary integer number. For that purpose we have to use successive division by 2 method. So now 2 divides 52 26 times, remainder is 0. 2 divides 26 13 times, remainder is 0. 2 divides 13 6 times, remainder is 1. 2 divides 6 3 times, remainder is 0. 2 divides 3 1 time, remainder is 1. 2 divides 1 0 times, remainder is 1. Okay, the successive division by 2 method, the given decimal integer number is successively divided by 2 until the quotient is 0. Okay, whenever the quotient 0 is obtained, now we have to read the remainders from bottom to top. So from bottom to top, remainders, first 1, second 1, third 0, fourth remainder 1, fifth remainder 0, sixth remainder 0. So this is the equivalent binary integer number for the decimal integer number. Okay, so for that purpose we have to use successive division by 2 method. Successive division by 2 method use. Okay, so now we go for another example problem. So convert 105.15 base 10 into binary. Okay, so in this one this decimal number contains two parts. One is integer part and another one is fractional part. Now we have to solve this problem divided into two sub-problem. We have to separate integer part base 10 and we have to separate fractional part 0.15 base 10. Now we have to solve these two sub-problems separately. Once we are getting the result, then we have to combine these two sub-problems. Then we are getting the equivalent binary number. Okay, so this is the sub-problem 1 and this is the sub-problem 2. So we have to solve these two sub-problems individually. Once we are getting the result, then we have to combine the result of two sub-problems. Then we are getting the equivalent binary number for the given decimal number. Okay, now we go for 105. So 105 divides 2. So 52 times remainder is 1. Okay. 2 divides 52 26 times. So remainder is 0. Okay. 2 divides 26 13 times. Remainder is 0. 2 divides 13 6 times. Remainder is 1. 2 divides 6 3 times. Remainder is 0. 2 divides 3 1 time. Remainder is 1. 2 divides 1 0 time. Remainder is 1. Okay. Now we have to use successive division by 2 method. Successive division by 2 method. In this method, the given decimal number successively divided by 2 until the quotient is 0. Okay, once the quotient 0 is obtained, we have to read the remainders from bottom to top. So, remainders read from top to bottom. From bottom to top. Bottom to top. Okay. So now 1, next one is 1, next one is 0, next one is 1, next one is 0, next one is 0, next one is 1. So this is base 2 for the by decimal number 105 base 10. Okay, for that purpose we have to use successive division by 2 method. Now we go for second sub problem. So 0.15. So 0.15 is multiplied by 2 is equal to 0.30. We have to separate the integer part, that is 0. Okay. Now 0.30 into 2, that is equal to 0.60. Integer part is 0. Now 0.60 into 2, so that is equal to 1.20. Separate the integer part 1. Remaining fraction part 0.20 into 2, that is equal to 0.40. Here integer part is 0. Now 0.40 into 2 is equal to 0.80. Here fraction integer part is 0. Now 0.80 into 2 is equal to 1.60. Separate the integer part. The remaining fraction part is 0.60 into 2, that is equal to 1.20. Separate the integer part 1. The remaining fraction part 0.20 into 2, that is equal to 0.40. 40. Here the integer part is 0. Okay, here the same thing is repeated. Okay, so at that time, so there is no, here the integer part is 0, but fraction part does not get 0 value. Okay, whenever the same sequence is repeated, then we have to stop that procedure and read the integer parts from top to bottom. Okay, so top to bottom, here 0, next one is 0, next one is 1, next one is 0, next one is 0, next one is 1, 1, 0. So this is the equivalent binary number for the fraction part. So that is 0.15 base 10. Okay, so this is the second subproblem. So this is first subproblem. Okay, once we are getting the result of two subproblems, then we have to combine them. So result is equal to so 105.15 base 10 is equal to integer part result is 1101001 point, decimal part result so 001001110. This is the equivalent binary integer number for the given decimal integer number. Okay, so here this is first subproblem. The first subproblem result is this one. The second subproblem result is this one. Now we have to combine these two subproblems result for getting the original answer. Okay, so 105 plus 0.15, that is 105.15 base 10 is equal to, so this problem result is this one and this problem result is this one. Then we have to combine by using the decimal point. So this is the integer part result and this is the fractional part result. Okay, so for this given decimal number, this is the equivalent binary number. Okay, now we go for another example problem. Now in this video also we have to solve some example problems. So that is extension to previous videos. Okay, so now example 3 problem, convert 45 base 10 to binary number using the DIVVELA method. So it contains only a decimal integer number. To convert this decimal integer number into equivalent binary integer number, we have to use successive division by 2 method. Okay, so here first we have to take the given decimal integer number. So it successively divided by 2 until the quotient is 0. So that is 2 divides 45 22 times, remainder is 1. 2 divides 22 11 times, remainder is 0. Now 2 divides 11 5 times, remainder is 1. 2 divides 5 2 times, remainder is 1. 2 divides 2 1 time, remainder is 0. 2 divides 1 0 time, remainder is 1. Okay, in the successive division by 2 method, the given decimal integer number is successively divided by 2 until the quotient is 0. So whenever the quotient is 0, okay, read the remainders from bottom to top. So read reminders from bottom to top. Bottom to top. Okay. So now, so 45 base 10 is equal to equivalent binary integer number can be obtained by reading the remainders from bottom to top. Now 1, 0, 1, 1, 0, 1. So this is the equivalent binary integer number for 45 base 10. Okay. So in this problem we have to use successive division by 2 method. Successive division by 2 method. Division by 2 method. Okay. Next we go for this example problem. So here this is a decimal fraction part. Okay. To convert this decimal fraction number into binary number, we have to use successive multiplication by 2 method. Okay. So that is 0.625 is successively multiplied by 2. So that is equal to 1.25 is 0. Okay. Here we have to separate the integer part 1. The remaining fraction part is 0.250 into 2. So that is equal to 0.50. The fraction part is 0.50. Integer part is 0. Now we have to take the fraction part 0.50 into 2. So that is equal to 1.00. We have to separate the integer part 1. The remaining fraction part is 0. Whenever the fraction part becomes 0, now we have to read the remainders from top. We have to read the integer parts from top to bottom. Okay. So that is first one, next one 0, next one 1. So point before that one point we have to use. So this is base 2. Here 0.625 base 10 is equal to 0.101. Okay. So read integers from top to bottom. Top to bottom. Okay. Here use successive multiplication by 2 method. Multiplication by 2 method. Okay. So the first in this third example only decimal integer part is there. In the fifth example fractional decimal part is there. Now observing this example 4, it contains both the integer part and fractional part. Okay. Now, so whatever the solution we are used, okay, this successive division by 2 method we have to use it for converting the given decimal integer number into binary integer number. Here also we have to use successive multiplication by 2 method for converting decimal fraction number into equivalent binary integer number. Okay, binary fractional number. So here we have to use successive division by 2 method for 163 base 10. Okay. Use successive multiplication by 2 for 0.875 base 10. Okay. So after that we have to combine these two results of these two methods for getting the original binary number for the given decimal number. Okay, now we have to take decimal integer number 163. Okay, so 163 is divides 81 times, remainder is 1. So 2 divides 81 40 times, remainder 1. 2 divides 40 20 times, remainder is 0. 2 divides 20 10 times, remainder is 0. 2 divides 10 5 times, remainder is 0. 2 divides 5 2 times, remainder is 1. 2 divides 2 1 time, remainder is 0. 2 divides 1 0 time, remainder is 1. Okay. In successive division by 2 method, we have to divide the given decimal integer number by 2 until the quotient is 0. So these are the quotients and these are the remainders. Whenever the quotient 0 is obtained, we have to read the remainders from bottom to top. Okay. So now 163 base 10 is equal to, read the remainders from bottom to top. So now 1 0 1 0 0 0 1 1. So base 2. Okay. Now we are taking the fraction number. So that is 0.875 is multiplied by 2. In successive multiplication by 2 method, is the given decimal fraction number is multiplied by 2 until the fraction part of the product becomes 0. Whenever the fraction part of the product is 0, then we have to read the integer parts from top to bottom for getting the equivalent binary number. Okay, 0.875 is equal to 1.750. Okay, so separate the integer part 1. The remaining fraction part is 0.750 into 2. So that is equal to 1.50. Separate the integer part 1. Next one, 0.50 into 2 is equal to 1.00. Separate the integer 1. Whenever the fractional part becomes 0, then we have to stop the procedure and read the remainders from and read the integer parts. So this is integer part, and read the integer parts from top to bottom. So top to bottom. So therefore 0.875 base 10 is equal to 0.111. From top, this one and this one. Base 2. Okay. So this is the first subproblem result. This is the second subproblem result. So therefore the final result is equal to, so 163.875 base 10 is equal to 163 base 10 plus 0.875 base 10. So that is equal to 163 base 10 result is 101,000,11 base 2 plus 0.111 base 2. So that is equal to 101,000,1.112. Okay, so this is the result 163.875 base 10. Okay, this is the final result. So in this way, we have to solve the given decimal integer number into binary integer number by using successive division by 2 method, decimal fraction number into binary fraction number by using successive multiplication by 2 method. So this number is a mixture of integer number and fraction part. At this time, we have to combine both methods, successive division by 2 method and successive multiplication by 2 method. So we have to solve this subproblem into 2 subproblem. This is the first subproblem result and this is the second subproblem result. After getting the result of first subproblem and second subproblem, okay, then we have to combine the result of both subproblems. Finally, we are getting the result of this subproblem. 163.875 is equal to, so this result plus this result. This is the original result. Okay, this is the final answer. Final answer. Okay, so thank you for watching this video. If you like this video, please share this video to your friends and classmates. If you like this video, please subscribe my channel and give valuable comments. So my channel name is DIVVELA SRINIVASA. Thank you. Hi friends, today I am giving a lecture on decimal to hexadecimal conversion. It is one type of conversion in number conversion in digital logic design, or switching theory and logic design. Okay, so suppose we are given a decimal integer number. To convert this decimal integer number to hexadecimal integer number, for that purpose we have to use successive division by 16 method. In this method, the given decimal number is successively divided by 16 until the quotient is 0. Once the quotient 0 is obtained, the remainders are read from bottom to top. Then it gives the equivalent hexadecimal number for the given decimal integer number. Okay. Second method is successive multiplication by 16 method. So this method is used for converting the decimal fraction number into equivalent hexadecimal number. So in this method, first we have to multiply the given decimal fraction number by 16. Whatever the result we are getting, from that result we have to separate the integer part and fraction part. Integer part can be written one side. Whatever the fraction part, that fraction part again multiplied with 16. So whatever the result we are getting, from that result we have to separate the integer part and fraction part. Okay, this process is continued until the fraction part becomes 0 or repeated a number. So once we are getting the fraction value either 0 or repeated number, then we have to write the integer numbers from top to bottom. That gives the equivalent hexadecimal fraction number for the given decimal fraction number. Okay, so this method is also called as hexadecimal method. Okay. Third type, suppose we are given a decimal number. To convert this decimal number into equivalent hexadecimal number, that decimal number contains both the integer part and the fraction part. For the integer part, we have to use successive division by 16 method. For fraction part, we have to use the successive multiplication by 16 method. Then we have to combine both method results for we are getting the equivalent hexadecimal number for the given decimal number. Okay, now we go for some example problems. Example 1, convert 2598 base 10 to hexadecimal number. This is a decimal integer number because its base is 10. There is no decimal point is there. So it is a decimal integer number. To convert this decimal integer number into hexadecimal number, we have to use successively division by 16 method. Okay, so now we have to take 2598. This is a decimal integer number. We have to divide by 16 in successive division by 16 method. So 16 ones, 16, 16, 6, 96, 16, 1, 16, 66, 38, 16, 2. So remainder is 6. Okay. Next one is 16 tens. So remainder is 2. And 16 zeros. 0. Remainder is 10. In hexadecimal number, 10 can be written as capital A. So therefore, A is equal to 10. Okay. So here, once the quotient 0 is obtained, we have to write the remainders from bottom to top. Remainders read from bottom to top. Okay. So therefore A to 6. A to 6. Base 16 for the given decimal number 2598 base 10. Okay. So for the given decimal integer number 2598 base 10, the equivalent hexadecimal numbers are A26 base 16. So here uses successive division by 16 method. Successive division by 16 method. Okay. Successive division by 16 method. Okay. Next, we go for second example. Convert 0.675 base 10 to hexadecimal. This is a decimal fraction number. So to convert this decimal fraction number to hexadecimal, we have to use successive multiplication by 16 method. So we have to use successive multiplication by 16 method. Method. Okay. So therefore 0.675 into 16. So that is equal to 16 5 80, 16 7 112, 112 plus 8 120, 12 is there, 16 6 96, 96 plus 12, so that is 108. So 108 means 10.5 Okay, now we have to take the integer part is 10. 10 can be written as capital A in hexadecimal system. Okay, now 0.80 into 16, so that is 0, 16, 8, 128, so 128, 8.12. Okay, so 12 can be written as C in hexadecimal number. Here 10 can be written as capital A, 12 can be written as capital C, because 10 is not there in hexadecimal system, 12 is not there in hexadecimal system. So here A is equal to 10, here C is equal to 12. So now it is again 0.80, so that is equal to again 12.80, that is C. Now integer part can be separated, 12 can be separated, here 12 is equal to capital C. Okay, now again 0.80 into 16, that is equal to 12.80. 12 can be separated, integer part can be separated. In hexadecimal system, 12 can be written as capital C. Okay, so here the same value can be repeated. Now we have to stop the procedure for multiplying the fraction part by 16. Okay, so now write the reminders from write the integer parts, write the integer parts from top to bottom. So now 0.8cc base 16 for the given decimal fraction number, 0.675 base 10. Okay, here we have to use successive multiplication by 16 method. So the given decimal fraction number is multiplied with 16, we are getting 10.800. Here the integer part and fraction part can be separated. So the integer part is 10. In the hexadecimal number system, 10 is not there, then it can be represented by capital A. So therefore A is equal to 10. Now the fraction part is 0.800 is multiplied with 16, we are getting 12.80. Now the integer part can be separated. In hexadecimal system, 12 is not there, so 12 can be written as C. So here C can be written as 12. So 0.80 again fraction part is multiplied with the 16, we are getting 12.80. We have to separate the integer part, so that is 12. 12 can be written as capital C. Now the remaining part is 0.80 is multiplied with the 16, we are getting 12.80. Now the integer part can be separated and fraction part can be separated. In the hexadecimal number system, 12 is not there, 12 can be written as capital C. So here the same value can be repeated. So at that time we have to stop the procedure until the given accuracy is obtained. So now write the integers from top to bottom, then we are getting the fraction part 0.ACC base 16 for the given decimal fraction number 0.675 base 10. Okay, now third problem, convert 2598.675 base 10 to hexadecimal number. This problem is a combination of this problem and this problem. So directly we are writing the result. Here we have to use two methods, successive division by 16 method for integer part, successive multiplication by 16 method for fraction part. Whatever the result we are getting in this problem and whatever the result we are getting in this problem, both are combined in this problem. So therefore, the result is, so A to 6, that is the integer part result, fraction part result, that is capital A, C, 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 base 10 for the given decimal number 2598675, base 10. Okay. So in this way, we have to solve any problem. Next, we go for example problem 4. Convert 423 base 10 to hexadecimal. Here, the given decimal number is a decimal integer number. There is no fraction part is there. So for that one, we have to use successive division by 16 method. Okay, in this method, we have to divide the given decimal number successively by 16 until the quotient is 0. Once the quotient 0 is obtained, we have to read the remainders from bottom to top. That gives the equivalent hexadecimal number for the given decimal number. So now, 423 divided by 16. So 16 2s and 16 6. Remainder is 7. Next one, 16 1s 16. So remainder is 10. 10 can be written as capital A. Okay. Now 16 zeros, a remainder is 1. So once we are getting the quotient 0, so read the remainders from bottom to top. Here 16 divides 423 26 times, the remainder is 7. 16 divides 26 one time, the remainder is 10. 10 can be written as capital A in hexadecimal number system. 16 divides 1 0 time, remainder is 1. Once the quotient is 0, now these remainders can be written from both remainders. Read from bottom to top. Bottom to top. So that is equal to first remainder 1, second remainder capital A, third remainder 7. 1A7 base 16 for the given decimal number 423 base 10. Okay. So this is the answer. Here we have to use successive division by 16 method. Okay. So next problem, example 5. Convert 2479 base 10 to hexadecimal. Here it is also a decimal integer number. To convert this hexadecimal number, so we have to use successive division by 16 method. So therefore 2479 base successively divided by 16. 16 ones 16, 16 fives 80, 16 fours 64. Remainder is 15. 15 can be written as capital F in hexadecimal number system. So next one is 16 nines 144. So remainder is 10. 10 can be written as capital A in hexadecimal number system. 16 divides 9 0 time, a remainder is 9. Okay. So once the quotient is 0, then write the remainders from bottom to top. So therefore 9AF base 16 for the given decimal number 2479 base 10. Okay, this is the answer. Here we have to also use successive division by 16 method. Okay. Now we go for example 6. Convert 49056 base 10 to hexadecimal and to binary. First we have to convert the given decimal integer number to hexadecimal number. Once we are getting the hexadecimal number, that hexadecimal number can be converted into binary. So in this way we have to solve this problem. First, here we have to also use successive division by 16 method for the given decimal integer numbers. This is the given decimal integer number. So in this successive division by 16 method, we have to divide the given decimal number by 16 until the quotient is 0. So this is 16 3s 48, 0, 16 6 and 16 6. Remainder is 0. Now 16 1s 16, 16 9s 144 and 16 1s 1. Remainder is 10. 10 can be written as capital A in hexadecimal number system. Here 16 12s 192, 16 1s 16 11s, so that is 176. The remainder is 15. 15 can be written as capital F. Next 16 zeros, then it is capital B. 11 can be written as capital B. Okay. So once we are getting the remainder quotient is 0, read the remainders from bottom to top. Read the reminders from bottom to top. So that is equal to B F A 0 base 16 for the given decimal integer number 49056 base 10. Okay. So here 16 divides 49,056 by 3066. The remainder is 0. 16 divides 3066 191 times. Remainder is 10. 10 can be written as capital A in hexadecimal number system. 16 divides 191 11 times. Remainder is 15. 15 can be written as capital F in hexadecimal number system. 16 divides 11 0 times. Remainder is 11. 11 can be written as capital B in hexadecimal number system. So once the quotient is 0, the remainders are read from bottom to top. So then BFA0 base 16. So this is the equivalent hexadecimal number for the given decimal number. Here we have to use successive division by 16 method. Now this hexadecimal number BFA0 base 16 to binary. Okay. To convert this hexadecimal number into binary, so each and every digit in the hexadecimal number converted into 4-bit binary group, because 16 can be written as 2 power 4. So 4-bit binary group can be treated as one digit in hexadecimal number system. So each and every digit in the hexadecimal number can be represented by 4-bit binary group. Then we are getting the equivalent binary number for the given hexadecimal number. Okay. So each and every digit in hexadecimal number is converted into 4-bit binary group. 4-bit binary group. Okay, so now DFA0. So capital B is nothing but 11. So 11 can be written as 1011. Capital F is nothing but 15 in hexadecimal number system. The equivalent binary is 4 ones. Capital A is 10. So 10 can be written as 1010 in binary. Next, 0 can be written as 4 zeros. Okay. So each and every digit in the given hexadecimal number can be converted into 4-bit binary group. Okay. Once we are converted into 4-bit binary group for the given hexadecimal digit in the hexadecimal number, now we have to combine all the 4-bit binary groups. So that is 1011. So 4 ones. Next 1010. Next one 4 zeros. So this is the equivalent binary number for the given hexadecimal number. So BFA0 base 16. Okay. So now the conclusion is, so the given hexadecimal number, the given decimal number is 49056 base 10. So this is the given decimal number. For this given decimal number, the equivalent hexadecimal number is BFA0 base 16. For this given hexadecimal number, the equivalent binary number is 1011 4 ones, 1010 4 zeros. So base 2. So this is the result. So this is the given decimal number. For this given decimal number, the equivalent binary number is this one. For this given decimal number, the equivalent hexadecimal number is this one. Okay. So in this way, we have to solve the given decimal number is converted into equivalent hexadecimal number. Okay. Thank you. Thank you for watching. If you like this video, please share this video to your friends and classmates and give your valuable suggestions. Please subscribe my channel name. So DIVVELA SRINIVASA. Thank you. Hi friends. Today I am giving a lecture on decimal to octal conversion. It is one type of conversion in number conversion in digital logic design, overall switching theory and logic design. Okay. Now, what is the procedure we have to follow for converting given decimal number into octal number? So for that purpose, we have to use two methods. First one is successive division by 8 method. Second one is successive multiplication by 8 method. In successive division by 8 method is used for converting the given decimal integer number into equivalent octal integer number. Okay. So in this method, we have successively division the given decimal number until the quotient is 0. Whenever the quotient is 0, then the remainders can be read from bottom to top gives the equivalent octal number for the given decimal number. Okay, so this is the successive division by 8 method. Okay, so this is the given decimal number. To convert this decimal number into equivalent octal number, we have to use successive division by 8 method. Okay, so in this method, the given decimal number is successively divided by 8 until the quotient is 0. These are all our quotients until the quotient is 0. Whenever the quotient 0 is obtained, okay, we have to read the reminders from bottom to top. So these are the reminders. The reminders can be read from bottom to top, then it gives the equivalent octal number for the given decimal number. Okay, so 5497, 8 divides 5497 687 times, the remainder is 1. Okay, 8 divides 687 85 times, the remainder is 7. 8 divides 85 10 times, the remainder is 5. 8 divides 10 1 time, the remainder is 2. 8 divides 1 0 times, the remainder is 1. So whenever the quotient 0 is obtained, this is 0. Whenever the quotient 0 is obtained, read the remainders from bottom to top. Bottom to top. Then it gives 12571. 12571 is the equivalent octal number for the given decimal integer number. Okay, so this is the successive division by 8 method. Next, second method is successive multiplication by 8 method. This method is used for converting the given decimal fraction number into equivalent octal fraction number. Okay, in this successive multiplication by 8 method, the given decimal number is multiplied with the 8. Okay, then whatever the number we are getting, from that number we have to separate the integer part, then whatever the remaining part, fractional part we are getting, again it is multiplied with 8. Okay, then we have to separate the integer part and the fraction part. Now again the fraction part is multiplied with the 8. Okay, until the fraction part getting 0 value. Okay, once we are getting the fraction part value 0, we have to read the integers from top to bottom. It gives the equivalent uh, octal fraction number for the given decimal fraction number. Okay, now this is the example. This is the decimal fraction number 0.635 base 10 to octal number. Okay, to convert this decimal fraction number into octal number, we have to use successive multiplication by 8 method. In successive multiplication by 8 method, we have to multiply the given octal decimal fraction number with the 8. So 0.635 is multiplied with 8. We are getting 5.080. Here this is the 0.080 is the fraction number. Integer number is 5. Now we have to separate the integer number from this number. So 5 is separated. What is the remaining fraction number? 0.080 is again multiplied with 8. We are getting 0.640. here integer part is separated 0, the remaining fraction part 0.640. Again it is multiplied with 8, we are getting 5.12. Okay, so separate the integer part 5, and what is the remaining part? 0.12. 0.12 is multiplied with 8, we are getting 0.96. We have to separate the integer part 0, the remaining fraction part 0.96 is multiplied with 8, so that is 7.68. We have to separate the integer part 7, the remaining fraction part 0.68 is multiplied with 8, we are getting 5.44. Separate the integer part, the remaining fraction part 0.44 is multiplied with 8, we are getting 3.52. We have to separate the integer part 3, the remaining part 0.52 is multiplied with 8, we are getting 4.16. Separate the integer part 4, the remaining part 0.16 is multiplied with 8, we are getting 1.28. Separate the integer part 1, the remaining part 0.28 is multiplied with 8, we are getting 2.24. Separate the integer part, then we are getting 0.24 is multiplied with 8, we are getting 1.92. Separate the integer part 1. So the remaining part is 0.92 is multiplied with 8, we are getting 7.36. Separate the integer part 7, the remaining part 0.36 is multiplied with 8, we are getting 2.88. Separate the integer part 2, in the remaining part 0.88 is multiplied by 8, we are getting 7.04. Is separate the integer part 7, the remaining is 0.04 is multiplied with 8, we are getting 0.32. Separate the integer part 0, 0.32 is multiplied with 8, we are getting 2.56. Separate the integer part 2. Okay, so in this problem we are not getting the fraction part 0. Okay, so now we have to, now we whenever the given accuracy is obtained, then we have to stop the procedure whether the fraction part contains the 0 value or not. Okay, so now we have to stop this procedure, then read the integers from top to bottom, so then we are getting the equivalent octal number for the given decimal fraction number. Okay, octal fraction number for the given decimal fraction number. In this way, we have to solve this problem by using successive multiplication by 8 method until the fraction part contains the 0 value or the required accuracy is obtained. Okay, to convert the mixed number that contains both integer part and fraction part. Okay, to convert the given decimal number that contains both integer part and fraction part, so at that time we have to use both methods, that is successive division by 8 method separately for a integer part, successive multiplication by 2 method for fraction part, then we have to combine the result of both successive division by 8 method for integer part, successive multiplication by 8 for fraction part, then we are getting the equivalent octal number for the given decimal number. Okay, now this is the given example. Convert 378.93 base 10 to octal. So here 378 is the integer part and 0.93 is the fraction part. Okay, for this integer part, for converting the given decimal integer number to octal number, we have to use successive division by 8 method. To convert the fraction decimal fraction number to equivalent octal fraction number. For that purpose, we have to use successive multiplication by 8 method. So this result and this result we have to combine for getting the equivalent octal number for the given decimal number. Okay. In successive division by 8 method, so 378 divided by 8. So 8 fourths, so that is 32, and 8 sevenths, 56. So remainder is 2. So 8 fives, remainder is 7. So 8 zeros, remainder is 5. Okay. So whenever the quotient is 0, then read the remainders from bottom to top. Okay. Read remainders from bottom to top. Bottom to top. Okay. 8 divides 378 by 47 times. A remainder is 2. 8 divides 47 5 times. Remainder is 7. 8 divides 5 0 times. Remainder is 5. So therefore 378 base 10 is equal to 572 base 8. Okay. Here we use, so this method is successive division by 8 method. Successive division by 8 method. Okay. For the only decimal integer part. Now we go for decimal fractional part. It is multiplied by 8. So 0.93 into 8. So that is equal to 8 3 24, 8 9 72 74. So 7.44. We have to separate the integer part 7. Now 0.44 is multiplied with 8. 8 4 32, 3. 8 4 32, 35, 3.52. Separate the integer part, that is 3. The remaining part is 0.52 into 8. So that is equal to 8 to 16. 8 5 40, 40 plus 1, 41. So that is 4.16. Separate the remainder integer part. So 4, the remaining fraction part is 0.16 into 8. So that is equal to 1.28. Separate the integer part 1. So that is 0.28 into 8. So that is equal to 2.24. Okay. Separate the integer part 2. Now 0.24 into 8. So that is equal to 1.92. Separate the integer part 1. Okay. So now 0.92 into 8. So that is equal to 8 to 16. 7.36. So that is 7 separated. Now 0.36. Okay. So there is no point of getting the fraction part 0 in 0.93 base 10. Okay, at that time we have to stop the procedure and read the integer parts from top to bottom. Okay, read integers from top to bottom. Okay, so this method is successive multiplication by 2. Successive multiplication 7341217 base 8. So that is equal to 0.93 base 10. Okay. Now we have to combine this result and this result. So therefore 378.93 base 10 is equal to the result 572.7341217 base 8. This result and this result we have to combine. Here this is 0.734127. So this is 572 plus 0.7341217. So 572.7341217. This is the equivalent octal number for the given decimal number. Okay. Now we go for another example problem. Convert 266 base 10 to octal. So that is 266 is successfully divided by 2 until the quotient is G2. Okay. So 8 3s 24, 8 3s 24. So remainder is 2. Okay. Now 8 4s remainder is 1. Now 8 0 remainder is 4. Okay. So whenever the quotient is 0, read the remainder from bottom to top. So that we are getting 412 base 8 is equal to 266 base 10. Okay. Bottom to top. Read remainder. Read remainder from bottom to top. Okay, we are getting 412 base 8 for the 266 base 10. Now we go for another example. So 146. So 8 ones, 8 eights. So that is remainder is 2. So 8 twos, remainder is 2. 8 zeros, remainder is 2. So read the remainders from bottom to top. Read remainders from bottom to top. Bottom to top. So now the result is 222 base 8 for the given of decimal number 146 base 10. Okay. In this way, we have to solve the given decimal number into equivalent octal number. Okay. So thank you. Thank you for watching this video. If you like this video, please share this video to your friends and classmates. If you like this video, please subscribe my channel name. So DIVVELA SRINIVASA. DIVVELA SRINIVASA. Hi friends, today I am giving a lecture on decimal number to excess-3 code conversion. In this conversion, we have to given decimal number, then the corresponding excess-3 code is obtained by adding +3 to each and every digit in the given decimal number. Okay, here for every digit in the given decimal number, we are adding +3 to get the equivalent excess-3 code number. Okay, so now we go for example, convert each of the following decimal numbers to excess-3 code. Okay, so the first bit is 9. Okay. So this is the given decimal number 9. For this given decimal number, the equivalent accessory code is obtained by adding +3. Okay. So here we are given 9. For the equivalent accessory code obtained by adding +3. So then we are getting 9 plus 3, that is equal to 12. Okay. Therefore, accessory of decimal number 9 is 12. So 12 is nothing but 1100. Okay. Next, second bit 37. The given decimal number is 37. The equivalent accessory code is obtained by adding +3 to each and every digit. Here the given decimal number, there are 2 digits are there. So one digit is 3 and another digit is 7. For each and every digit we have to add +3. Okay. So here 3 plus 3, that is 6, and 7 plus 3, that is 10. Okay. So here the corresponding binary number is, the corresponding accessory code is 1100. Here the corresponding accessory is 0110. 10 means 1010. Okay. So therefore, accessory of decimal number 37 is 01101010. So this is the answer. Okay. Next one. Next we go for third bit. In the third bit, the given decimal number is 82. In that one, there are 2 digits are there, digit 8 and digit 2. For each and every digit, we have to add +3 to get the equivalent accessory code. Here 8 is there, here 2 is there. We have to add +3 for each and every digit. So 8 plus 3 is 11 and 2 plus 3, that is 5. Okay. So here the corresponding accessory code is 11 accessory code is 1011. 5 is 0101. Okay. So therefore, accessory of decimal number 82 is we have to combine these two, 1011 0101. Okay, so this is the accessory code of decimal number 82. Okay, next one we can go for fourth bit. In that one there are 3 digits are there. Each and every digit we have to add +3. So that is 1, 4, 5. We have to add 3. We have to add 3. We have to add 3. Okay. So 1 plus 3 is 4. The corresponding binary number is 0100. Next here +7. The corresponding binary number 010111. Next 5 plus 3, that is +8. The corresponding binary number is 1000. Okay. So now we have to combine all these bits. So therefore, accessory of decimal number 145 is 0100 011 1000. So this is the answer. Okay. Now we go for this one. The given decimal number is 9203. Okay. For each and every digit in the given decimal number, we have to add 3. After that, the corresponding number can be converted into binary. Then we have to combine all the binary digits. Okay. So here 9203. Here we have to add plus 3. Here we have to add plus 3. Here we have to add plus 3. Okay. So 9 plus 3, that is 12. The corresponding binary number 1100. Okay. 2 plus 3, that is plus 5. The corresponding binary number 0101. 0 plus 3 is 3. The corresponding binary number 0011. 3 plus 3, that is 6. The corresponding binary number 0110. So therefore, excess3 of decimal number 9203 is 1100 0101 0011 0110. So this is the excess 3 of 9203. Next one, excess 3 of decimal number 28. Here there are two digits are there, 2 and 8. For each and every digit we have to add plus 3. So here 2 plus 3, that is 5. The corresponding binary number is 0101. 8 plus 3, that is 11. The corresponding binary number is 1011. Okay. So then, therefore, excess 3 of code, excess 3 of decimal number 28 is 0101 1011. So this is the excess 3 code of decimal number 28. Okay. Next one, what is the excess 3 code of decimal number 247.6? How many number of digits are there? Before the decimal point 3 digits, after the decimal point 1 digit is there. So for each and every digit we have to add plus 3. So here 247.6. Okay. We have to add plus 3. We have to add plus 3. We have to add plus 3. Point. We have to add plus 3. So 2 plus 3, that is 5. 4 plus 3, that is 7. 7 plus 3, that is 10. 6 plus 3, that is 9. Okay. The corresponding binary number is 0101. Here 0111. Here 1010. Point. Here 1001. Okay. So therefore, we have to put arrow. Okay. Next, therefore, excess 3 of decimal number 247.6 is, we have to combine all these binary digits 0101 0111 1010.1001. So this is the given excess 3 code of decimal number 247.6. Okay. So here the corresponding binary number, Okay. Here also the corresponding binary number. Next one, last one. So in this one, the given decimal number contains 4 digits. Before the decimal point 3 digits, after the decimal point 3 digits. Each and every digit in the given decimal number we have to add +3 to get the corresponding accessory code. So that is 359.4. We have to add +3, +3, +3, point, +3. So that is 6, 8, 12, point, that is 7. Okay. The corresponding binary code is 0110, 100, 0110, 0111. Okay. So therefore, accessory code of decimal number 359.4 is, we have to this one, combine all the binary digits 0110, 100, 1100, 0111. So this is the equivalent accessory code for the given decimal number. Okay, so thank you for watching this video. If you like this video, please share this video to your friends and classmates. If you like this video, please subscribe my channel name. So DIVVELA SRINIVASA.